Hey guys, tonight on Slumber Expeditions, we travel back tens of millions of years to witness the single greatest architectural project our planet has ever undertaken. This is not a story of human hands, but of continents in motion, a slow-motion collision of unimaginable force that gave birth to the most majestic and formidable mountain range on Earth, the Himalayas. This vast, sky-piercing wall of rock did more than just reshape the geography of Asia. It fundamentally altered the world's climate, redirected the course of evolution, and created a cradle for civilizations, all while hiding within its layers the definitive proof for one of science's most revolutionary theories. We will journey to the bottom of an ancient ocean to find the origins of these mighty peaks. We will feel the immense tectonic forces that thrust the seabed into the clouds and uncover the fossilized clues that revealed this incredible story. We will then explore how the rising mountains changed the very air of the planet, creating the monsoons and cooling the globe, setting the stage for the world we know today. So before you settle in, if you're finding comfort in these explorations of our planet's deep past, please consider liking this video and subscribing to the channel, but only if you genuinely like what we do here. We would also love to hear from you in the comments below. Tell us where you're listening from and what time it is there. It's always fascinating to connect with a global community of curious minds who share this fascination with Earth's grandest stories. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's geological journey together. You are floating in the warm, shallow waters of the Tethys Ocean some 150 million years ago, during the late Jurassic period. The sun is bright, filtering down through the clear, turquoise water onto a vibrant seafloor. This is not the deep, dark abyss of the open Pacific. This is a vast continental shelf, a submerged margin of the supercontinent Gondwana, which itself is a colossal landmass containing what will one day become South America, Africa, Antarctica, Australia, and India. The world is a different place. The air is thick with carbon dioxide, the poles are free of ice, and lush forests extend to the high latitudes. The configuration of the continents is alien. The Atlantic Ocean is just a narrow rift, and North America is still connected to Europe. In this world, the Tethys is a dominant feature, a great east-west seaway that separates the northern continents, known as Laurasia, from the southern supercontinent of Gondwana. Beneath you, the seafloor is a living tapestry of primordial life. Strange, ammonites with their intricately coiled shells drift by like fleet submarines, their tentacles searching for smaller prey. Their shells, displaying a stunning array of sutured patterns, will one day become the index fossils that allow geologists to date these ancient rocks with precision. On the bottom, thick mats of cyanobacteria and algae grow, and the skeletal remains of countless microscopic organisms, called foraminifera and coccolithophores, rain down continuously, building up a slow, steady, and immense layer of calcium carbonate on the ocean floor. This gentle, perpetual snowfall of biological debris is creating the limestone that will one day form the summit of Mount Everest. This is a peaceful, ancient world, a world dominated by marine reptiles like the long-necked plesiosaurs and the powerful, dolphin-like ichthyosaurs, a world entirely unaware of the forces gathering that will utterly obliterate it and push its very floor into the stratosphere. The engine of this coming change lies deep within the Earth, in a slow, convective churn of the mantle hundreds of kilometers below the placid sea surface. The planet's crust is not a single, unbroken shell. It is a dynamic jigsaw puzzle of tectonic plates, adrift on a sea of ductile, partially molten rock. Around 130 million years ago, during the early Cretaceous, a massive plume of superheated material begins to well up from the deep mantle beneath Gondwana, likely from the very boundary with the Earth's core. This upwelling, a mantle plume of immense power, acts like a geological blowtorch, weakening the continental crust from below and initiating a monumental rupture. The crust bulges and stretches, and eventually, a vast sliver of land, the Indian subcontinent, begins to break away from the eastern flank of Gondwana, where it was nestled between Madagascar and Australia. A new seafloor spreading ridge forms in a nascent ocean, and like a colossal, slow-moving conveyor belt, it begins to push India northward, across the Tethys Ocean, toward the waiting underbelly of the Eurasian landmass. The journey is slow, a matter of a few inches per year, but over millions of years, this adds up to thousands of miles. For the next 100 million years, India will be a solitary continent island, a ship of stone sailing across an ancient ocean, its prow aimed directly at Asia. As it moves, the oceanic crust of the Tethys floor is forced downward, sliding beneath the Eurasian plate in a process called subduction. This process is not smooth. It creates deep oceanic trenches and triggers violent volcanic activity along the Eurasian margin, forming a volcanic arc not unlike the modern-day Andes. The descending slab of oceanic crust, being denser than the underlying mantle, pulls the rest of the plate along with it in a process known as slab pull, which may have contributed to India's surprisingly rapid northward journey. Geologists estimate that India moved at speeds of up to 6 to 9 inches per year, a breakneck pace in geological terms, making it one of the fastest-moving continents in Earth's history. This race across the Tethys would set the stage for one of the most energetic collisions ever witnessed by our planet. But the main event, the collision itself, is still tens of millions of years in the future, a looming destiny written in the slow, unstoppable logic of plate tectonics. The evidence for this lost ocean and India's long journey is locked in the very rock of the Himalayas themselves. The story begins not with a mountain but with a fossil. In the early and mid-19th century, explorers and surveyors for the Great Trigonometric Survey of India began to map the high Himalayas. As they climbed into the dizzying heights, battling altitude and extreme conditions, they made a discovery that defied all logic and contemporary understanding of the world. There, embedded in the limestone cliffs at altitudes of 20,000 feet and more, on peaks like Mount Everest and the surrounding ridges, they found the fossilized remains of ancient marine creatures. These were not the bones of mountain goats or high-altitude birds. They were the unmistakable, spiraled shells of ammonites like the genus Baculites and the delicate, segmented imprints of trilobites, creatures that lived, fed, and died in a warm, shallow sea. The implication was staggering, almost heretical. The rock that now formed the highest peaks on Earth, the very roof of the world, had once been at the bottom of an ocean. This was the first major clue that the Himalayas held a secret far grander and more dramatic than anyone had imagined. The pristine, white limestone that caps Mount Everest, known today to geologists as the Komalengma Formation, is not a stone born of mountains. It is a marine limestone, a compacted graveyard of those ancient sea creatures from the Tethys Ocean. The summit of the world, the ultimate symbol of terrestrial height, was once a seabed, a testament to the unbelievable power of the forces that shaped our planet. The long, solitary voyage of the Indian subcontinent finally came to an end around 50 to 55 million years ago during the Eocene epoch. The leading edge of the Indian plate, a thick and buoyant mass of continental crust, began to encounter the southern margin of the Eurasian plate. This was not a sudden, catastrophic impact, like two ships colliding in the night. It was a slow, inexorable, geological embrace, relentless pushing that continues to this day, a force that has never ceased. The initial contact was likely not a single, defined point, but a complex series of interactions as the irregular coastlines, submerged shelves, and offshore island chains of the two landmasses began to touch and interact. Island arcs and microcontinents, such as the one that would later form the bedrock of much of Tibet, that lay in the central Tethys between them, were the first to be crushed, deformed, and sutured onto the growing southern edge of Asia. This process, known as accretion, built up the Eurasian margin in preparation for the main event. But the final, head-on collision between the two continental giants was unavoidable, a planetary-scale event set in motion 100 million years prior. When two oceanic plates collide, one slides under the other. When an oceanic plate meets a continental plate, the denser oceanic plate is subducted. But when two continents meet, a different and more dramatic process unfolds, one that defines the nature of the Himalayas. Continental crust, composed largely of granite, is too thick and too buoyant to be easily subducted back into the dense mantle. Instead of one plate sliding neatly under the other, the two land masses began to compress against one another like two immense, slow-motion sumo wrestlers. The immense force of the collision, with India acting as the relentless aggressor, had to be accommodated. Since the crust could not easily sink, the path of least resistance was upward and sideways. The sedimentary layers that had accumulated for hundreds of millions of years on the northern margin of India and on the deep floor of the Tethys Ocean were caught in this continental vice. They were scraped off the descending plate, folded, fractured, and thrust skyward in a series of immense, overlapping sheets, like a rug being pushed across a floor and piling up against a wall. This process, known as thrust faulting, is the primary architectural mechanism that built the Himalayas. Enormous slabs of rock, hundreds of miles long and many miles thick, were pushed one on top of the other along great horizontal faults, doubling and tripling the thickness of the crust in this colossal impact zone. One of the most significant of these is the main central thrust, a gigantic fault that placed deeply buried, high-grade metamorphic rocks from the core of the Indian continent on top of younger, less metamorphosed rocks. Above this lies the South Tibetan Detachment, a normal fault that allowed the upper layers of the mountains to stretch and slide southward as the pile thickened. The entire mountain range is a complex stack of these thrust sheets, a geological layer cake of monumental proportions. The energy required for this is almost beyond calculation. It is the energy of a continent's momentum, dissipated not in a single instant, but over tens of millions of years, through the slow, plastic deformation and brittle fracture of rock on a continental scale. The forces involved in this ongoing collision are a constant and powerful presence. The Indian plate is still moving northward into Asia at a geologically brisk rate of about 1.5 to 2 inches per year. This relentless push is responsible for the Himalayas continuing to rise, albeit at a rate of roughly half an inch per year that is nearly matched by the relentless forces of erosion from ice, water, and wind. But this movement is not smooth and continuous. The plates are locked together by friction along the massive fault lines for decades or centuries at a time, storing immense elastic energy in the deformed crust like a spring being compressed. When the accumulated stress finally exceeds the frictional force holding the rocks in place, the rocks slip, releasing that stored energy in the form of devastating earthquakes that ripple through the entire region. The entire Himalayan region, from the Hindu Kush in the west to the Arakan Yoma in the east, is one of the most seismically active zones on the planet, a testament to the titanic forces that are still actively shaping the landscape. The 2015 Gorkha earthquake in Nepal, which registered a magnitude of 7.8, and killed nearly 9,000 people, was a direct result of this ongoing collision, a sudden lurch as the Indian plate pushed just a little further beneath its Eurasian counterpart, releasing centuries of accumulated strain on the main Himalayan thrust fault. The mountains themselves are a record of countless such events over tens of millions of years, each tremor a small, violent adjustment in the planet's greatest and most ongoing geological project, a reminder that the Earth here is very much alive and in a state of constant, dynamic becoming. The story of the Himalayas is not just written in the grand scale of its peaks and the violence of its earthquakes. It is recorded in minute detail within its rocks, its fossils, and its very structure. Unraveling this story required a geological detective story that spanned centuries, piecing together clues that often seemed contradictory until the grand unifying theory of plate tectonics provided the final, missing piece of the puzzle. The marine fossils high on the peaks were the first major clue, but they were just the beginning of a much deeper and more complex narrative. The true revelation came from understanding the intricate architecture of the mountain range itself, and from a clever technique that could trace a continent's ancient latitude. Geologists mapping the Himalayas in painstaking detail discovered a consistent and revealing pattern in the rock layers, a pattern that told the story of the collision from its earliest stages to its most profound depths. They identified three primary, parallel geological belts running the entire east-west length of the range, each with a distinct character and history. In the south, bordering the fertile Gangetic Plains, are the Siwalik Hills, a relatively young range composed of sedimentary rocks like sandstone, mudstone, and conglomerates that are only 16 to 5 million years old. These rocks are the eroded debris of the rising mountains to the north, carried down by mighty rivers and deposited in vast alluvial fans. The Siwalik strata are a treasure trove of paleontology, filled with the fossils of ancient mammals that lived in the rivers and swamps at the foot of the young range, primitive elephants like Gomphotherium, giant tortoises, crocodiles, and early apes such as Civipithecus, a possible ancestor of the orangutan. North of the Siwaliks lies a zone of complex, highly folded and faulted rocks, known as the Lesser Himalayas. This belt is comprised of older Proterozoic and Paleozoic rocks, now transformed into low-grade metamorphic rocks like phyllite, slate, and schist, which were once ancient sediments that were heated, pressurized, and crushed during the initial stages of the collision. Further north still are the Great Himalayas, the core and backbone of the range, containing the highest peaks like Everest, K2, and Kangchenjunga. This belt is composed of incredibly old crystalline rocks, granites, gneisses, and high-grade metamorphic rocks like kyanite and sillimanite schists that represent the deep, ancient basement of the Indian continent, rocks that were once 20 to 30 miles deep within the crust but have been thrust upward and exposed by the colossal forces of the collision. This orderly progression from young sediments in the south to the ancient crystalline heart of India in the north paints a clear and powerful picture of the thrusting process, with layer upon layer being stacked up from the south, each major thrust fault bringing older, deeper rocks to the surface. The final, and perhaps most elegant, proof of the continental collision came from a field of study known as paleomagnetism. This technique relies on the fact that certain iron-rich minerals in volcanic rock, such as magnetite, act like tiny compass needles. When the rock is molten, these minerals are free to move, and they align themselves with the Earth's magnetic field. As the rock cools and solidifies, this magnetic orientation is frozen in time, permanently recording the direction to the magnetic North Pole and, crucially, the latitude at which the rock was formed. By drilling oriented core samples from ancient volcanic rocks across India and analyzing their paleomagnetic signatures in the lab, geologists were able to trace the subcontinent's path through geological time with remarkable precision. They found that rocks from the Deccan Traps in central India, a vast volcanic province that erupted about 66 million years ago, showed a magnetic signature indicating they formed at a latitude of about 30 degrees south of the equator. Younger rocks from northern India showed progressively more northerly latitudes. Today, India sits at around 20 degrees north. This data provided irrefutable, quantitative evidence that India had indeed traveled over 4,000 miles from deep in the southern hemisphere, crossing the equator on its journey to collide with Asia. The Himalayas were thus the ultimate validation of the then controversial theory of plate tectonics, a living, breathing demonstration of the power of continental drift written in stone and magnetic fields for all who knew how to read it. This monumental geological event did more than just create mountains. It created a stage for a new chapter in the story of life and a catalyst for global climate change. The creation of the Himalayas and the massive Tibetan plateau to their north coincided with a major global cooling trend that began around 50 million years ago and eventually led to the current ice age. As the mountains rose, they began to interact with the atmosphere in a profound new way. But their most direct biological impact was arguably on our own evolutionary lineage. The uplift of the Himalayas and the Tibetan Plateau, often called the third pole, created a massive rain shadow. The powerful monsoon winds, which carry moisture from the Indian Ocean, were forced to rise over this colossal barrier. As the air rose, it cooled, releasing its moisture as torrential rain on the southern slopes of the Himalayas, while the air that descended on the other side, over Central Asia, was dry and cold. This process began to dry out the climates of Central Asia and, through global atmospheric connections, East Africa as well. In Africa, the lush, extensive forests that had dominated the landscape for millions of years began to recede, replaced by open savannas and patchy woodlands. This dramatic change in environment, this opening up of the landscape, is believed by many paleoanthropologists to have been a key driver in forcing our primate ancestors out of the trees and onto the ground. The advantages of standing upright to see over tall grass, to travel more efficiently between scattered food sources, and to free the hands for carrying and tool use became critical for survival. The Himalayas, in a very real and indirect sense, helped to push humanity onto its own 2 feet, setting the stage for the eventual emergence of the genus Homo and, ultimately, our own species. The story of these mountains is not just a story of rock and time. It is inextricably linked to the story of us, a reminder of the deep and often unexpected connections between the geology of our planet and the evolution of life upon it. As we conclude this part of our journey into the making of the Himalayas, we like to extend a special thank you for listening. If you're finding comfort in these explorations of our planet's deep past, please consider liking this video and subscribing to Slumber Expeditions. We would also love to hear from you in the comments below. Tell us where you're listening from and what time it is there. It's always fascinating to connect with our global community of curious minds. You can also share which part of the story has captivated you the most so far. It would be wonderful to start a conversation around it. Now, let the immense scale of this geological drama settle in your mind as we prepare to continue our exploration. The rise of the Himalayas represents one of the most significant atmospheric engineering projects in Earth's history, a fundamental reworking of global climate patterns that transformed the Asian continent from a relatively uniform landscape into a region of dramatic climatic contrasts. This transformation occurred through the creation of the monsoon system, a seasonal reversal of winds so powerful that it dictates life for nearly half of the world's population. The monsoon is not merely a weather pattern that happens to occur near mountains. It is a direct physical consequence of the Himalayan uplift, a necessary atmospheric response to the presence of this colossal barrier disrupting the free flow of air across the continent. The system's complexity is breathtaking, involving interactions between ocean currents, atmospheric pressure cells, and the sheer physical bulk of the mountains themselves, creating a weather machine of planetary significance. The fundamental physics begins with differential heating between land and ocean, but the Himalayan system elevates this simple principle to an entirely new level of intensity. During the boreal spring, as the sun's angle increases, the vast continental mass of Asia begins absorbing tremendous amounts of solar energy. The Tibetan Plateau, with an average elevation exceeding 4,500 meters, plays a particularly crucial role. Its high, dark rock surfaces absorb solar radiation with extraordinary efficiency, heating the air immediately above it to temperatures far warmer than the free atmosphere at similar altitudes elsewhere. This creates what meteorologists call a thermal low, an immense, persistent area of low atmospheric pressure centered over the plateau that acts like a massive vacuum cleaner drawing in air from surrounding regions. Meanwhile, over the Indian Ocean to the south, the water's high heat capacity means it warms much more slowly, maintaining relatively higher atmospheric pressure. This stark pressure differential sets in motion the great summer monsoon circulation. Moisture-laden air from the ocean surges northward toward the continental low, but its path is blocked by the Himalayan wall. With nowhere else to go, this air is forced to rise. As it ascends the mountain slopes, it expands and cools adiabatically, and its moisture condenses into the torrential rains that characterize the monsoon season. The process is a perfect, large-scale demonstration of thermodynamics, where solar energy is converted into kinetic energy of wind and latent heat of vaporization, which is then released high in the atmosphere, powering the system further. The sophistication of this system reveals itself in its multiple interacting components. The South Asian monsoon isn't a single current, but a complex network of flows including the Somali jet, a low-level wind stream that accelerates across the Arabian Sea, and the tropical easterly jet, a high-altitude wind pattern that forms in response to the Tibetan heat source. The timing and intensity of monsoon onset are governed by intricate feedback loops involving sea surface temperatures in the Indian Ocean, snow cover on the Tibetan Plateau, and even dust aerosols from the Middle East. The orographic effect, the forced uplift of air over mountains, is dramatically amplified in the Himalayas due to their exceptional height and steepness. Some of the wettest places on Earth are found on the southern slopes of the eastern Himalayas, where towns like Cherrapunji and Monsoon in India can receive over 11,000 millimeters of rain annually, most of it during the monsoon months. The mountains don't just cause rain, they wring the atmosphere dry with unparalleled efficiency, creating an almost unimaginable hydrological contrast between the drenched southern slopes and the arid rain shadow regions of the Tibetan Plateau to the north. This rain shadow effect is so powerful that it creates the high-altitude desert conditions of the Tibetan Plateau, one of the most arid and inhospitable environments on Earth, just a few hundred kilometers north of the lushest rainforests. The monsoon's influence extends far beyond immediate rainfall patterns, creating ripple effects throughout the global climate system. The enormous latent heat released when water vapor condenses over Asia, a process that involves staggering amounts of energy equivalent to thousands of nuclear explosions daily, powers atmospheric waves that propagate around the planet, influencing weather patterns as far away as North America and Europe. The freshwater input from monsoon rains into the Bay of Bengal creates a distinct, low salinity layer that affects ocean circulation patterns and cyclone formation. This freshwater cap can inhibit the upward mixing of cold, nutrient-rich water, affecting marine productivity and potentially intensifying cyclones by keeping the ocean surface warmer. Perhaps most significantly, the erosion caused by monsoon rains drives the silicate weathering cycle that removes carbon dioxide from the atmosphere, creating a long-term cooling effect on global climate. The creation of the Asian monsoon represents a fundamental reorganization of Earth's heat and moisture distribution, with the Himalayas serving as the central catalyst in this transformation. Climate model simulations consistently show that without the Tibetan Plateau and Himalayas, the Asian monsoon would be a pale shadow of its current self, weaker, less seasonal, and unable to support the dense agricultural populations that have characterized Asian civilizations for millennia. The very rhythm of life, from the planting of crops to the flow of rivers that sustain cities, is a direct gift of this mountain-forged climate system. While the Himalayas were creating the monsoon system that dominates Asian climate, they were simultaneously setting in motion a much slower but ultimately more profound global transformation. The transition from the warm, greenhouse world of the early Cenozoic to the cool, icehouse world characterized by the glacial-interglacial cycles of the last few million years. This remarkable climatic shift, which saw ice sheets advance across North America and Europe, has its origins in the geochemical processes acting on the freshly exposed rocks of the rapidly uplifting Himalayas. The mechanism involves Earth's long-term carbon cycle, specifically the process of silicate weathering, which acts as the planet's primary geological thermostat over million-year timescales. This process demonstrates how the solid Earth, the atmosphere, and the hydrosphere are linked in a delicate dance that regulates the planet's temperature. This silicate weathering process begins when atmospheric carbon dioxide dissolves in rainwater to form weak carbonic acid. When this slightly acidic rain falls on the fresh, unweathered silicate minerals that are constantly being exposed by the rapid erosion of the Himalayas, it initiates a chemical reaction that converts atmospheric CO2 into dissolved bicarbonate ions. A simplified version of this complex geochemical reaction can be represented as calcium silicate plus 2 carbon dioxide molecules, 2 CO2 plus water, H2O, yield a calcium ion plus 2 bicarbonate ions plus silicon dioxide. The reaction describes the aqueous dissolution and carbonation of wollastonite, a type of chemical weathering. This reaction captures 2 molecules of atmospheric carbon dioxide for every 1 molecule of silicate rock weathered. These ions are then transported by rivers, most significantly the Ganges-Brahmaputra system, which carries more sediment than any other river system on Earth, to the ocean. In the marine environment, marine organisms like foraminifera and coccolithophores incorporate the bicarbonate into their calcium carbonate shells, CaCO3, and when these organisms die, their shells sink to the ocean floor, eventually forming limestone deposits that sequester the carbon for geological timescales. This process represents a net removal of CO2 from the atmosphere-ocean system, gradually reducing the greenhouse effect and cooling the planet. What makes the Himalayas particularly effective at driving this cooling is the combination of exceptionally high erosion rates, constantly exposing fresh, reactive mineral surfaces, and the intense monsoon rainfall that provides the water necessary for the chemical reactions and efficiently flushes the weathering products to the ocean. This system is a perfectly tuned negative feedback loop. Mountain uplift creates monsoons, which accelerate erosion and weathering, which draws down CO2 and cools the planet. The evidence for this Himalayan-driven cooling comes from multiple lines of geological investigation. Marine sediment cores show a dramatic increase in sedimentation rates in the Bengal Fan, the underwater delta formed by the Ganges and Brahmaputra rivers, beginning around 15 to 20 million years ago, coinciding with a period of accelerated Himalayan uplift known as the Neogene uplift. Geochemical proxies for past atmospheric CO2 concentrations, such as the boron isotopic composition of foraminifera shells and the alkanone unsaturation index from marine phytoplankton, show a general decline throughout the Cenozoic, with particularly steep drops correlating with periods of intensified monsoon and Himalayan tectonic activity. The timing is crucial. The long-term decline in CO2 created the necessary preconditions for polar ice sheet formation, which first appeared in Antarctica around 34 million years ago, when CO2 levels fell below approximately 750 parts per million, and in the Northern Hemisphere around 3 million years ago, when levels dropped further. Once atmospheric CO2 levels fell below a critical threshold, estimates suggest around 300 to 350 parts per million, the stage was set for the ice ages to begin. In this lower CO2 world, the relatively small variations in Earth's orbit and axial tilt known as Milankovitch cycles became sufficient to push the climate system across the threshold for glaciation, causing ice sheets to advance and retreat in regular cycles of roughly 100,000, 41,000, and 23,000 years. The global consequences of this Himalayan-driven cooling were transformative and laid the foundation for the modern world. The expansion of polar ice sheets during glacial periods lowered global sea levels by over 120 meters, exposing continental shelves and creating land bridges that allowed species migrations, including the peopling of the Americas across the Bering Land Bridge. The altered temperature gradients between equator and poles intensified atmospheric circulation patterns, creating stronger winds and more pronounced seasonality in many regions. The distribution of biomes shifted dramatically, with tropical forests contracting and grasslands expanding. In Africa, the cooling and drying trend is thought to have played a key role in the expansion of savanna environments at the expense of forests, creating the ecological context for hominin evolution and the development of bipedalism. The Himalayas thus functioned as a planetary climate control switch, their growth gradually turning down the global thermostat and reshaping not just Asian climate, but the entire Earth system. This illustrates the profound interconnectedness of solid Earth processes with atmospheric and biological evolution. A mountain range rising in one part of the world can ultimately influence global climate, sea level, and even the course of human evolution over millions of years. The Himalayas represent one of Earth's most spectacular natural laboratories for evolutionary processes, where extreme environmental gradients and complex topography have driven rapid speciation and produced extraordinary biological diversity. The region encompasses an astonishing range of ecosystems compressed into a relatively small area, from tropical rainforests at low elevations to permanent ice fields at the highest peaks, with temperate forests, alpine meadows, and arid steppes in between. This dramatic environmental compression, combined with the complex topography that creates numerous isolated sky islands, has made the Himalayas a biodiversity hotspot of global significance and a living demonstration of evolutionary principles in action. The mountains act as both a museum, preserving ancient lineages, and a cradle, generating new species at a remarkable rate. The primary engine of speciation in the Himalayas is allopatric speciation driven by topographic complexity. As the mountains rose, they fragmented once continuous populations of plants and animals into isolated subpopulations separated by high mountain barriers. The eastern Himalayas, particularly the region where the mountain range makes a sharp bend around the Namcha Barwis and Taxus, serves as a spectacular example of this process. Here, the Yarlung Tsangpo River cuts the world's deepest gorge, with vertical relief exceeding 5,000 meters over a horizontal distance of just 40 kilometers. This creates an incredibly steep environmental gradient that has driven explosive diversification in numerous groups. Rhododendrons provide a classic example, What was likely a single ancestral species has diversified into over 300 species in Himalayas, adapted to different elevations and microclimates, with variations in leaf morphology, flowering time, and cold tolerance that represent exquisite adaptations to specific niches along the mountain slopes. Similar patterns of radiation are evident in primroses, genus Primula, with over 120 species, and orchids, with an estimated 750 species in the eastern Himalayas alone. In the animal kingdom, this pattern repeats with pheasants like the spectacular Himalayan monal, frogs of the genus Sculpted, and butterflies like the Kaiser eye hind, each group showing remarkable diversification in response to the complex topography and climate gradients. The high-altitude environment of the Himalayas, particularly above 3,500 meters, has selected for some of the most remarkable adaptations in the animal kingdom. The snow leopard, Panthera uncia, exemplifies these adaptations with its compact, powerful body, thick, insulating fur with a density of up to 4,000 hairs per square centimeter, wide, snowshoe-like paws that distribute its weight on snow, and enormously long tail that serves both as a balancing organ for navigating rugged terrain and as a wraparound blanket in extreme cold. Its nasal cavities are exceptionally large, providing more surface area to warm and humidify the thin, frigid air before it reaches the lungs. Perhaps even more extraordinary are the physiological adaptations of species like the Himalayan tar and various pika species that thrive in oxygen-depleted environments above 4,000 meters. These animals have evolved hemoglobin with higher oxygen affinity, more efficient cellular metabolism, and specialized behaviors for conserving energy during the long, harsh winters. The bar-headed goose, which migrates over the highest peaks, possesses physiological adaptations including a more efficient oxygen extraction system in its lungs and hemoglobin with a particularly high affinity for oxygen that allow it to extract oxygen from the thin air at altitudes that would render most birds unconscious. These adaptations are not mere curiosities, they are sophisticated solutions to the extreme challenges of high-altitude life, refined over millions of years of natural selection. For humans, the Himalayas have served as both a formidable barrier and a corridor for migration and cultural exchange. The mountains marked the southern boundary of Tibetan civilization and the northern limit of South Asian cultural influence, creating a mosaic of ethnic groups with distinct languages, religions, and subsistence strategies adapted to specific altitudinal zones. The Sherpa people, for instance, developed a unique culture and economy centered around high-altitude trade and, later, mountaineering support, while other groups like the Gurums and Timans developed sophisticated terrace farming systems on steep slopes. Perhaps the most fascinating human dimension of Himalayan adaptation involves the physiological responses of indigenous populations to high-altitude hypoxia. Tibetan highlanders have evolved genetic adaptations, particularly variants of the EPS1 gene that regulate hemoglobin production, that allow them to thrive at altitudes above 4,000 meters without developing the polycythemia, excess red blood cell production, that afflicts lowlanders at high elevation. Similar but genetically distinct adaptations have evolved in Andean populations, providing a remarkable example of convergent evolution in human populations facing similar environmental challenges. Research has shown that the Tibetan EPS1 variant was actually inherited from our ancient Denisovan cousins through interbreeding, a stunning example of how modern humans acquired beneficial traits from other hominin species. The Himalayas thus represent not just a theater of biological evolution, but of human biological and cultural evolution as well, where the challenges of high-altitude living have left their mark on the genetic makeup of human populations, and where geographical isolation has preserved cultural diversity that is rapidly disappearing elsewhere in the world. This makes the region an irreplaceable repository of both biological and cultural heritage, all shaped by the relentless uplift of the world's highest mountains. As we conclude this part of our journey into the atmospheric and biological legacy of the Himalayas, we'd like to extend a special thank you for listening. If you're finding comfort in these explorations of our planet's deep past, please consider liking this video and subscribing to Slumber Expeditions. We would also love to hear from you in the comments below. Tell us where you are listening from and what time it is there. It's always fascinating to connect with our global community of curious minds. You can also share which part of the story has captivated you the most so far. It would be wonderful to start a conversation around it. Now, let the profound interconnectedness of rock, sky, and life settle in your mind as we prepare to conclude our exploration. The story of the Himalayas extends far beyond geology and climate into the very heart of human civilization, where these mountains have served as the great hydrological engine powering some of humanity's most enduring cultures. The relationship represents one of geography's most profound examples of environmental determinism, where the availability of water, the richness of soil deposited by mountain rivers, and the protective barrier of the peaks themselves created the precise conditions for early civilizations to emerge, flourish, and develop complex cultural traditions that continue to shape modern societies. The Himalayas didn't merely provide a backdrop for human history. They actively wrote significant chapters of it through their control of water systems that determined where and how civilizations could develop across southern Asia. The Indus Valley Civilization, recognized as one of the world's 3 earliest cradles of civilization alongside Mesopotamia and ancient Egypt, offers compelling evidence of this fundamental relationship. Flourishing between 3300 and 1300 BCE across what is now Pakistan and northwest India, this remarkably sophisticated urban culture developed exclusively along the Indus River and its 5 major tributaries, the Jhelum, Chenab, Ravi, Beas, and Sutlej, all of which trace their headwaters to the Himalayan watershed. The civilization's extraordinary achievements, including meticulously planned cities like Mohenjo-daro and Harappa with their advanced drainage systems, standardized weights and measures covering a vast trading territory, and early forms of writing, were fundamentally enabled by the predictable seasonal flooding of the Indus River system. These annual floods, fed by the methodical melting of winter snows and the monsoon rains collecting in the Himalayan ranges, deposited rich mineral silt across the floodplains, creating agricultural surpluses that supported urban populations estimated at up to 5 million people at its zenith. The civilization's eventual decline around 1900 BCE has been linked by numerous scholars to climate change that altered the patterns of these Himalayan-fed rivers, either through diminished flow as precipitation patterns shifted or through catastrophic flooding as glacial lakes burst their boundaries, demonstrating the profound dependency of even the most advanced civilizations on the hydrological stability provided by the mountain system. Archaeological evidence shows settlements gradually shifting eastward toward the Gangetic Plain as the Sarasvati River, once a major Himalayan-fed waterway mentioned in Vedic texts, began to dry up, forcing populations to follow the receding waters. The Ganges River basin represents perhaps the most dramatic and enduring example of Himalayan influence on human settlement patterns and cultural development. As the Himalayas rose and the monsoon system intensified over millions of years, the Ganges River system evolved into one of the most fertile and densely populated regions on Earth, often described as the cradle of Indian civilization. The river's immense sediment load, derived from the ongoing erosion of the highest peaks including minerals from the metamorphic core of the mountains, has built a vast alluvial plain up to 300 kilometers wide, with soil depths exceeding 2,000 meters in places, creating some of the most productive agricultural land on the planet. This extraordinary geological gift created what would become the heartland of successive Indian empires, from the Mauryan and Gupta empires to the Mughal and British Raj, and the spiritual cradle of Hinduism, Buddhism, and Jainism. The river's profound spiritual significance and Hindu tradition, personified as the goddess Ganga, whose descent from heaven to earth was broken by Shiva's matted locks in the Himalayas to prevent the river's immense power from destroying the earth, reflects an intuitive understanding of the river's Himalayan origins and its dual nature as both life-giver and potential destroyer. The practical management of these waters led to early engineering marvels, including sophisticated irrigation systems, stepwells, and water storage facilities dating back to the Mauryan Empire in the 4th century BCE, with later Mughal rulers developing this into an extensive network of canals that transformed agricultural productivity across the northern plains. The development of philosophical concepts like Dara, the earth, and Jala, water, as fundamental elements in Indian philosophy, and the integration of river worship into religious practice can be seen as profound cultural reflections on this essential relationship between land, water, and human existence mediated by the Himalayan system. Beyond the Indian subcontinent, the Himalayan water system influenced civilizations across Southeast Asia through the Mekong, Irrawaddy, and Salween rivers, all of which originate on the Tibetan plateau. The Khmer Empire, with its magnificent capital at Angkor, developed sophisticated hydraulic engineering to manage the seasonal fluctuations of the Tunnel South Lake and Mekong River system, creating a vast network of reservoirs, canals, and embankments that supported one of the medieval world's largest pre-industrial settlements. Similarly, the various Burmese kingdoms that flourished along the Irrawaddy River developed complex social and political structures to manage the agricultural potential unleashed by the Himalayan waters, with the pagan kingdom constructing an extensive system of weirs and canals that turned central Burma into the rice bowl of Southeast Asia. The mountains thus served as a hydrological hub whose influence extended thousands of kilometers downstream, supporting civilizations across South and Southeast Asia through a network of rivers that functioned as natural highways for trade, migration, and cultural exchange, while simultaneously providing the water and fertile sediments necessary for agricultural surplus. This relationship continues today with even greater significance, with the rivers originating from the Himalayas supporting approximately 1.5 billion people, nearly 20% of the world's population, who depend on them for drinking water, agriculture, industry, and energy production. The historical pattern is unmistakable and profound. Wherever the Himalayan waters flowed, civilization followed, creating a direct lineage from the tectonic forces that built the mountains to the cultural and technological achievements of humanity in their shadow, a relationship that continues to shape regional politics, economics, and culture in the contemporary world. The Himalayas have played a pivotal role not just in shaping human civilizations, but in revolutionizing human understanding of the planet itself. The mountain range served as the ultimate natural laboratory and proving ground for the theory of plate tectonics, providing the conclusive evidence that transformed continental drift from a controversial hypothesis into the fundamental paradigm of modern earth sciences. The story of how the Himalayas validated plate tectonics represents one of the most important chapters in the history of science, demonstrating how careful observation of a specific geological feature can illuminate global processes and overturn long-established scientific dogmas, ultimately reshaping our understanding of how our planet works. The journey toward understanding began with the systematic observations of European geologists during the colonial period, who were immediately struck by the scale and structural complexity of the Himalayas. British geologists like Henry Benedict Medlicott and William Thomas Blandford working for the Geological Survey of India in the late 19th century, conducted pioneering surveys that documented the extraordinary folding and faulting visible throughout the mountain range. They recognized the basic sequence of rock formations, from the young sediments of the Siwalik Hills in the south to the highly metamorphosed rocks of the high Himalayas, but lacked a theoretical framework to explain how such structures could form. The prevailing geosynclinal theory, which posited that mountains formed through the gradual sinking and compression of sedimentary basins, seemed increasingly inadequate to explain the Himalayan scale and complexity, particularly the presence of high-grade metamorphic rocks overlying less metamorphosed sequences. It was the work of Swiss geologist Augusto Ganser in the 1930s and 1940s, particularly his comprehensive 3-year geological study of the Himalayas documented in his seminal work, Geology of the Himalayas, that first clearly documented the massive thrust faults, especially the main central thrust, that placed older rocks over younger ones. A structural relationship that defied conventional geological wisdom and hinted at previously unimaginable horizontal crustal movements. Ganser's meticulous fieldwork, conducted under extraordinarily difficult conditions, revealed a structural architecture that simply couldn't be explained by vertical movements alone, pointing toward massive horizontal compression of the crust. The critical breakthrough came with the development of paleomagnetic techniques in the 1950s and 1960s, which provided the quantitative evidence needed to demonstrate continental motion beyond reasonable doubt. British geophysicist Keith Runcorn and his colleagues collected rock samples from the Deccan Traps and other geological formations across India and analyzed their preserved magnetic signatures. Their findings were revolutionary. The magnetic minerals in rocks of different ages pointed to different magnetic pole positions, creating an apparent polar wander path that indicated India had migrated thousands of kilometers from the southern hemisphere since the Cretaceous period. When these paleomagnetic data were combined with the emerging understanding of seafloor spreading from oceanographic research, particularly the magnetic striping patterns on the ocean floor discovered by Drummond Matthews and Fred Vine, they provided irrefutable evidence that India had indeed raced northward as a discrete continental plate before colliding with Asia. This explained not only the Himalayan formation but also the exceptional speed of India's movement, up to 15 to 20 centimeters per year during the late Cretaceous, making it one of the fastest-moving continents in Earth's history, a finding that initially stunned the geological community. The Himalayas thus became the textbook example of continent-continent collision, the missing piece that connected the evidence for seafloor spreading with the theory of continental drift, finally providing a comprehensive mechanism for how continents could move across the Earth's surface. In the decades since this breakthrough, the Himalayas have continued to serve as a natural laboratory for refining our understanding of plate tectonic processes. The development of sophisticated geophysical techniques, including deep seismic profiling and continuously operating GPS networks, has allowed scientists to create detailed three-dimensional images of the ongoing collision that would have been unimaginable to earlier geologists. We now know that the Indian plate continues to plunge beneath the Eurasian plate at a shallow angle of only 10 to 15 degrees, a process called underthrusting, which explains the pattern of earthquakes and the continued uplift of the Tibetan Plateau. The discovery of ultra-high-pressure metamorphic minerals like coesite and microdiamonds in Himalayan rocks provided direct evidence of continental material being subducted to depths of over 100 kilometers before being rapidly exhumed, a process previously thought impossible for buoyant continental crust. The Himalayas have also been crucial for understanding how plate tectonics interacts with climate systems. The uplift of the range and Tibetan Plateau altered atmospheric circulation patterns, which in turn affected erosion rates that feed back into the tectonic system through isostatic rebound and sediment loading. This ongoing research has transformed the Himalayas from a geological curiosity into the definitive case study for continent-continent collision, a dynamic system that continues to shape both the Earth's surface and our understanding of its deep workings, proving that sometimes the keys to understanding global processes lie in the intensive study of specific, extraordinary places. As we enter the Anthropocene, the relationship between humanity and the Himalayas is entering a new and precarious phase that threatens to unravel the delicate balance that has sustained civilizations for millennia. The mountain system, often called the third pole because it contains the largest volume of ice and snow outside the polar regions, is experiencing some of the most rapid and comprehensive climate change on Earth, with profound implications for both regional stability and global climate systems. Understanding the vulnerability of the Himalayan system is essential not only for the nations directly dependent on its waters, but for the global community facing the interconnected challenges of climate change, water security, food production, and geopolitical instability in one of the world's most densely populated regions. The most visible and alarming impact of climate change in the Himalayas is the rapid and accelerating retreat of its glaciers, which function as natural water towers for the continent. Scientific studies using multiple methods including satellite imagery, ground observations, and repeat photography have documented that the vast majority of Himalayan glaciers are thinning and receding at rates that have alarmed the scientific community. The Hindu Kush Himalayan region has lost significant ice mass since the 1970s, with current loss rates approximately double those of the previous century, and some studies suggesting that even if global warming is limited to 1.5 degrees Celsius above pre-industrial levels, the region will still lose one-third of its glaciers by 2100. This glacial retreat has multiple cascading effects across the hydrological system. It initially increases river flow during melt seasons as more ice melts, raising the risk of flooding, including catastrophic glacial lake outburst floods, but eventually leads to reduced dry season flow as the glacial water towers diminish, creating a classic boom and bust water scenario. This pattern creates what scientists call peak water, the point at which meltwater contribution reaches its maximum, after which many river systems will experience progressively reduced flow. For the Indus, Ganges, and Brahmaputra river systems, which derive 30 to 50% of their dry season flow from glacial melt, this represents an existential threat to water security for hundreds of millions of people. The timing of this peak water varies by basin, with some western Himalayan catchments potentially having already passed this point, while eastern systems may reach it later this century, creating a rolling crisis across the region as different river systems pass this critical threshold at different times. Beyond glacial melt, climate change is disrupting the delicate hydrological balance of the Himalayan system in other critical ways that compound the challenges. Changing precipitation patterns are altering the monsoon rhythm that has governed agricultural cycles for millennia, with evidence suggesting an increase in extreme rainfall events alongside changes in the timing and distribution of seasonal rains, making water availability less predictable for farmers who have developed cropping patterns over generations based on reliable monsoon timing. The warming climate is also affecting the cryosphere beyond glaciers. Permafrost thaw at high altitudes is destabilizing mountain slopes, increasing the frequency of landslides and rockfalls that threaten infrastructure, settlements, and hydropower projects throughout the region. The formation and stability of glacial lakes are changing dramatically, with the number and size of potentially dangerous glacial lakes increasing significantly as glaciers retreat and leave behind moraine-dammed lakes. These lakes, dammed by unstable moraines composed of loose rock and debris, can burst catastrophically, causing devastating glacial lake outburst floods, GLOFs, that can wipe out villages, infrastructure, and farmland dozens of kilometers downstream with little warning. The 2013 Kedarnath disaster in the Indian state of Uttarakhand, which killed thousands and destroyed numerous temples and villages, demonstrated the deadly potential of such events, which are expected to become more frequent as climate change accelerates and more glacial lakes form in destabilized landscapes. The human implications of these changes extend far beyond immediate environmental impacts to touch on fundamental issues of regional security, international relations, and human migration patterns. The Himalayan water system sustains agriculture that feeds nearly 1 billion people, and changes in water availability could trigger mass migrations from rural to urban areas, agricultural collapse in regions dependent on specific water timing, and social unrest as communities compete for diminishing resources. The transboundary nature of most major Himalayan rivers, flowing through multiple countries with often tense political relationships, creates potential for water wars as nations compete for diminishing resources and attempt to secure water security through infrastructure projects that affect downstream flows. China's construction of major dams on the Brahmaputra, which it calls the Yarlung Tsongpa, has raised concerns in downstream India and Bangladesh, while India's water development projects similarly affect Pakistan, creating a complex web of hydrological interdependence that adds a layer of complexity to already delicate geopolitical relationships in one of the world's most densely populated and nuclear-armed regions. The future of the Himalayas thus represents one of the most critical challenges of the Anthropocene: how humanity will manage a shared, vital resource that is being fundamentally transformed by our collective actions, requiring unprecedented levels of international cooperation, scientific monitoring, and adaptive water management. The mountains that have shaped so much of human history through their geological, climatic, and hydrological influence now face a future being shaped by humanity, creating a profound responsibility for stewardship of this irreplaceable global heritage that will test our collective wisdom, foresight, and capacity for cooperation in the coming century. As we conclude our journey through the epic story of the Himalayas, we like to extend a special thank you for listening. If you found comfort in these explorations of our planet's grandest processes, please consider liking this video and subscribing to Slumber Expeditions. We would also love to hear from you in the comments below. Tell us where you're listening from and what time it is there. Connecting with our global community of curious minds is always fascinating. Now, let the profound legacy of these mountains, as shapers of continents, climate, and civilization, settle in your mind as we bring this expedition to a close.